Well, about the title, I have two different handouts and I have two different titles. The reason is that that's not my fault. The graduate student is so smart, like by the time I submit an abstract and by the time I present, things have changed. There are a lot more results to show. So I was tempted to last night and I managed to make the slide last night, despite that hard work. That's a different title. If I'm for that, I'm sorry. So out of 6 talks, there are 4 of them over the Arctic, right? And this is the first time I'm taking you to the South Pole, to the Antarctic. So a part of the talk, I'll talk about some part of climate science that you guys know, and some part of the data science that you guys know. So it's like in a hybrid talk. I'll try to explain as simple as possible so that everybody can understand. The slide. Okay, the reason people look at Arctic because they have been melting for a long time, known, and people working a lot on that. And Antarctic, on the other hand, was gaining like sea ice till 2014, 2015. And some people are trying to look at why their ice is growing. They should be melting. They were worried about the ice growth. And finally, they started melting. And they started melting in a way like last year, that was the record minimum over the Antarctic Southern Ocean. Record minimum sea ice noticed 32% less than what that should be. So now that's a concern because Antarctic region it stores like 200 feet of fresh water. If we completely melt that, 200 feet of sea level rise. So but it's important to know sea ice does not contribute to sea level rise because it's a glass of water. We put some sea ice on that, smells, nothing happens. But why that important? That is important because that actually acts as a buffer from mechanical forces or thermal forces that protects, like a blanket, like a not the warming blanket, a cold blanket, so that the sea ice sheets do not melt. Now they are melting, and surprisingly, that's not as a problem. Now the bigger problem is that Antarctic was losing an ice mass of around 146 billion tons per year. But last 2019, 2020, 2021, there have been like 300, 570 from 250 gigatons from there is a flow chart, not flow chart, there is a time series data from the NASA website. And so that's a concern, like sea ice started melting and we are seeing like a higher acceleration of the ice sheet loss about the Antarctic that can store 200 feet of water, sea level rise, equivalent to 100 feet of sea level rise. That's kind of concerning, and because 60% of us we live near 100 kilometer of the coastline somewhere in the world, 60% of us. So that's really an alarming thing. So it is still not well understood, like what's causing that and how that's going to affect the ice sheets over there. So let me give you the final goal of the project that we have been working on, me, Vandana, and the graduate student. Like the final goal is to understand this figure we see here. Take this out. The brown color shows the loss of sea ice sheets, and that's where the sea ice have been retreating recently. So we are trying to see if there is an association between sea ice loss and the ice sheet loss. I don't know that. Maybe there is an association. That's the next part that we are looking at. And maybe I was talking to Anis, like if we can find some association, maybe what's causing it, if that's happening. So we're trying to find out that. Going to something about the CNN, what we did, we went up to the max pooling and mean pooling operations. What we did, like we took like a matrix calculation of 2x2 grids kernel. So 4 grids become 1. Then we pull 2x2 stride 2x2. So like ultimately you can imagine each grid is 25 kilometer by 25 kilometers. So it's like 100 kilometer by 100 kilometer area after till the pooling layer. And we're trying to find out the maximum sea ice loss and the mean sea ice loss. If they are close to each other, that means that's an anomalous melting. So we're not looking at individual grids. We're looking at like combination of a 4x4 grid, at least 100 kilometer by 100 kilometer area. And the max pooling, mean pooling is close. That means that's it. And anomalous melts happening. We can talk about that later if you want to, but for the sake of time, I'll move on. And we did some, the problem is we need to find 2 things. One is anomalous melting, and then the clusters of anomalous melting. So not only like in the matrix profile does like grid by 1 grid, we wanted to look at like sometimes 1 grid can melt a lot, but in a neighborhood is nothing happening. So you wanted to look at clusters of melt, anomalous melting, huge amount of area loss. So we did a benchmark data that I had and we compared with that. So in terms of finding a clusters of anomalous melting or sea ice retreat. If you have anything, any study like that, the CMAD that the graduate student develop based on the inverse max pooling. It's talking about max pooling, but max pooling does not work here because we are talking about sea ice retreat, negative values. So something like a minimum pooling or inverse max pooling we did. Because if we do max pooling, maximum of negative value is close to zero. So we didn't want that. We didn't want a maximum or minimum, maximum CI is lost. So that's why we developed CMAD, convolutional matrix anomaly detection. And that's how it looks like. If you look at like September 8, 2022, every 7 days, we keep tracking the accumulate or cumulative anomalous melt. And you can see like how they start growing. The anomalous melt begins at the outer surface of the sea ice, and then gradually they keep moving and intensify with time. They move towards inland, more toward the land surface, and also the number increases. It is identified by the CMAD algorithm. And how good is the detection? So the red line is the sea ice extent, and blue line is the number of anomalous melts detected. So if you see, whenever we have low sea ice, we have higher number of anomalous melting. If we have higher number of sea ice, we have low anomalous melting. So they are negatively correlated, which makes sense. Now, why that is so important? I'm talking about anomalous melting, why not steady state melting? So from 2000 to 2023, the bar shows area lost because of the anomalous melting. So quite a significant, but if you see the line, that's the um, if you have the yearly maxima minus yearly minima, the total ice lost in that year. And if we divide that, that line shows like 70 to 80% of the melting is because of the anomalous melting detected in CNN. So that's why it's so important. Now, another fact is that the number of anomalous melting is increasing day by day. This is the trend, which says like most of the regions we have like at least one anomalous melting per year increasing. So it means for 23 years over a grid, you can expect like a 23 anomalous melting happening nowadays compared to back in 2000 or 2003. And similarly, the total number, if you just combine them, total number of anomalous melting, there are a lot more in numbers nowadays. So anomalous melting causing 70 to 80% melt over that region are increasing in numbers. So that's concerning. Maybe, I don't know, could be one of the reasons now why CI serve. Also, the first day of anomalous melting, it's also changing. There's when the anomalous melting starts, and the red line shows over the Ross and Bell-Emerson region. The melt onset melt onset is earlier than it used to be. Whereas that's the growth onset, where it says the growth of the anomalous growth of sea ice is delayed now over the Weddell region. So two different regions about two reasons about two different regions. And now we try to also use that in inverse max pool in full CNN to predict, taking each year out, leave 1 year out at a time. And you can see it did a pretty good job. Whenever we have high red or sea ice extent is high, we still predict less amount of blue. That means anomalous melting. If we have sea ice melting, if you have less sea ice and we have higher anomalous melting predicted. So method works pretty good. And yeah, that's to, sorry, how do I go back? Yeah, that's to conclude that. So CNN, the max pooling layer operation was able to detect the anomalous melting pretty well, and it matched with the negatively correlated almost all the time with the sea ice extent. And they begin to start melting at the outer boundary of the sea ice, gradually move inland, which makes sense too. And anomalous growth is delayed over the Weddell region, where the anomalous melting is early over the Bell-Emerson and Ross region. So we need to look more on that. And so, yeah, if you still manage to not sleeping yet, so we have a poster on patch CNN to predict sea ice. This is the max pooling operation, so patch CNN, like chop the images. So you have a poster, please see our poster today. And so with that, I can help. I'm happy to take any question if you have. Thank you.
And I think so you mentioned about the different clustering algorithm like dbScan, k-means, and but you were showing the table of the F1 score accuracy. Are you doing clustering or classification? And also clustering have a spatial clustering, temporal clustering, depend on what the goal of it. So what are how the clustering actually play a role in the overall target? Thank you.
So in the benchmark data, we try to identify the anomalous amount of transport, mass transport. Okay, aerosol atmospheric river. So the data I know, I know that what the transport's happening. We try to cluster the regions where the anomalous transport happening, 1.5 below higher than the upper bound. So that was one method, and then we also tried to match a matrix profile to find out anomalous transport happening. But we had to cluster. Either you detect the anomalies, then cluster, but these CMAD, or because of the convolution layer, then pooling layer, it automatically clusters the region and give you where the anomalous values are. So it's actually serving two purposes at a time.
Thanks, Sudip. Nice work. I was wondering in terms of additional variables that you could consider, both related to sea ice as well as the ice sheet mass loss, would you look at surface winds, surface temperatures, and how they are related to?
No, that's the next step of that graduate students after the defense's proposal. So we're looking at the association, like what's if first of all, is sea ice loss and ice sheet loss are associated with each other?
Yeah.
If they are, what's causing it? Maybe it's the wind, the sea surface temperature.
Yeah.
Many things. I mean, we can chat on later, like the features, like we need to, the next step is finding the association. If there is, next step is to find what's causing these or the features or parameters. Yeah, you can chat on that. Yeah.
Thank you.
Yes. Yeah. Thanks for nice talk. I'm just curious whether this effort related to the upcoming HDR Emerald Challenge, and the topic is about anomaly detection. And I knew that iHARP also contribute to one of the project.
Yeah, go ahead. Yeah, I think we went with the sea level rise data, not that one. Yep. Thank you.